This is Oliver,
And yeah, I'm Rachit.
and this
Welcome to
is
the
TheForkJoin.
TheForkJoin. Yeah, we
Welcome,
can't thank you enough
Sam.
for this. Thank you. Welcome, Sam. Yeah. So I guess this is the first time we're doing this, so we should do brief introductions for the host and then a longer introduction for our guest Sam. So I'm Rachit. I'm a final year PhD student at Cornell, although I'm spending my time in Boston. I work on programming languages and computer architecture and compilers and stuff like that.
Okay, I'm the other host, Oliver. I'm a first year or I guess I'm coming into second year PhD
Right.
student at University of Washington. I also work in programming languages and this sort of thing. So I'm very excited to be chatting with other people in research, getting interesting questions from chat, and learning a lot. So, hello. And then, Sam, do you want to introduce yourself?
Sure. So yeah, I'm Sam Westrick. I'm a postdoc at Carnegie Mellon University in Pittsburgh, and just finished my PhD about almost a year ago. And I do research on programming languages, on parallel computing, on parallel algorithms, somewhere in the intersection of algorithms and programming languages and systems. Um, yeah, so glad to be.
Awesome.
Yeah,
Yeah, and there's a secret reason why Sam is our first guest, which we'll get to eventually. But yeah, before we get into sort of the technical stuff, I guess I'm curious about, what got you into computing in the first place, and what got you into your PhD and the kinds of stuff that you're interested in today. Might be a
yeah,
very good question.
yeah. I I started doing robotics in high school, and I had this really great physics teacher who, like, he was interested in everything. I mean, he was our physics teacher, but like he was fiddling with GPUs on the side, and he was getting people to program like the robots with LabVIEW and like that kind of stuff. And I had a couple friends also who were kind of getting interested in the same stuff, and they were getting interested in programming the TI calculators, like the TI 84, 84, 83, I can't remember. But it had this like terrible little programming language in it, and you could create these little games on the calculator
Yeah,
where
it's
you could.
TI Basic, right? I
Yeah,
remember
TI Basic. Yeah, yeah,
making some little things in there, yeah.
yeah. And and so we would try to make little things, and I tried to write some programs for Lego Mindstorms also, and that kind of stuff. So like back in high school, I like started to get interested into this stuff, but that was not what I was planning to do at first at all. I went into school for music actually,
Oh,
and
nice.
and I but when I got there, I knew I was like, oh, this programming stuff is like kind of interesting. So I took a intro programming course when I arrived at CMU at Carnegie Mellon for undergrad, and I really liked it. It was so much fun. I ended up spending more time on the programming course, I think, than I did like practicing my instrument, which wasn't so great. Um, but I was still like, okay, I'm a music major, and like, so I like went for it and like did. I was a music major for 2 years while I was taking programming courses on the side. And eventually I was like, nah, I gotta switch. Like I was just liking it too much. And it was also probably a better financial choice to switch into computer science as well from music. So
Yeah.
yeah, so at that point I got involved with TAing a lot. So I became a teaching assistant for in the undergrad program at Carnegie Mellon. And there's a particular course that I TA'd for. It's called 15210. The full name is Parallel and Sequential Data Structures and Algorithms. It's a fairly unique course. It's not really taught anywhere else except for CMU, maybe a little bit elsewhere, but uh, it's a little, I guess, 10 years ago when it kind of like emerged into the CMU curriculum, or maybe 15 years ago. I can't remember how long it's been around. It was in some sense kind of an experimental course because it was a core curriculum course. It was like a sophomore level
Oh,
course that
it's
was
core. I see.
yeah,
Is
core
it still a
curriculum.
core curriculum?
Yep, still core curriculum.
Okay.
Um, so it's kind of experimental in multiple ways. It teaches parallel computing. It focuses on functional programming, and there's a very heavy emphasis on algorithm analysis, right? So take all of that and throw it together into one course, and that's a core curriculum course for CMU undergrads. Um, and it's probably like it's like the brainchild of Guy Blelick, of Amotakar. Amotakar is my supervisor now at CMU. But also people like Bob Harper at CMU who have a big influence in terms of functional programming and standard ML. So we started using standard ML in this course. And originally, the course was pretend it's parallel. We're going to teach you parallel algorithms using functional programming. But like, okay, standard ML that happens to not have an implementation that's really suitable for running things in parallel, right?
I see.
So everything was pretend it's parallel, but we can still write algorithms and we can analyze them and and so like if we want to get students to write parallel programs, you don't have to run them in parallel. You can still write them, right?
Right.
Even though we don't have a compiler that can actually back it up. Well, anyway, I loved this course. I thought it was amazing. I TA'd it like 8 times in a row, like way too many times in a row. Uh, I liked it so much, and it turned into my PhD research. So so after I finished my undergrad, then I started as a PhD student at CMU, working with Amut, who was one of the instructors for that course, but then he became my advisor. And the project that was kind of like put in my lap was, let's make a parallel version of standard ML. Now I should say that this was a project that I sort of inherited from previous students as well, right? That were working at CMU. So there's lots of people that have worked on this project, not just me. But it turned into my PhD thesis, and it turned into a whole memory management project. I mean, that was in some sense the original motivation. People had like tried to make parallel functional programming work. I mean, there's a lot of good examples of it working for sure. Like, I shouldn't say that it didn't work before what we did. It did work, okay? But like, everybody runs into the same problem, which is memory management. And I think, had a fresh approach to this problem and got a lot of success out of it.
And the language is called that you work on?
Well, okay. What is it called? That's a good question. I mean, the compiler is called Maple. And I think that we're a little bit fast and loose, and we say that the language is called Maple sometimes too, right?
I see.
Other times we say the language is called Parallel ML, because it's just standard ML plus parallel. So there you go. Yeah, but the compiler that we've been developing is called Maple, or MPL, because it turns out that the name Maple also refers to a lot of other software already. We didn't really look carefully into that before we named it.
Naming is hard, right?
We gave it a name. We're like, all right, good enough. And I liked the initialism MPL because it's like ML with a P in the middle and P for parallel and like. Yeah. So
does
maybe we'll call it MPL just to be clear on
let's call it MPL.
Some math software called.
Yeah. So does the course now use MPL?
They do. Yeah.
Okay. Great.
They use it for. They don't use it in all of the assignments because programming is not the main emphasis. Like algorithm analysis is the main emphasis. So we use it in the course in order to kind of like get people excited about thinking about parallel algorithms. Right. And they will write a little bit of code and I mean, they write actually a lot more code for the assignments, but not all of them we run through Maple. You don't need to run all of them through Maple. I mean, some of them are sequential algorithms too. Right. The course is called Parallel and Sequential, data structures and algorithms. So, just as much as we're teaching parallel merge sort, we're also teaching sequential, like Dijkstra's algorithm and A star and who knows. So it's like a core algorithms course in addition to parallel programming. Yeah.
Yeah, there's this maybe we're jumping into technical stuff too early, but I think you pointed out this insight that I think people new to parallel programming or people just starting out often forget, that you look at parallel programming and you always think about the compute. You're like, how do I take my compute and split it up into small tasks that I can go and push off and sort of run in parallel? But really, like, you also need to think about data and memory. You need to figure out a way to separate them. In the case of like a garbage collected language, you need to figure out how to allocate and collect all of these things automatically, right? And so like this is sort of a theme that seems to have come up over and over. For example, I'm sure you know about Emery Berger's work on the scalable malloc implementation horde. So I guess I'm curious about, could you tell us a bit about the history of that work, where that was originating from, if you're familiar with it, and like what is lacking? Because my understanding of even that work was that it was coming from a place where they were trying to build a scalable parallel programming model. Maybe not fully functional in the way Maple is, but what are the different choices and the trade-off space here when you were thinking about this problem?
Yeah, definitely. So are you curious specifically about like there's a lot of work on scalable memory allocation, for example.
Right.
And so memory allocate. So I think like there's this big bundle of topics, which we might broadly say is like memory management. Okay. But it's super broad and there's tons of different aspects to it. And one aspect of it is scalable allocation, right? In terms of like parallel memory management. Like how do you get a bunch of different computers or different threads on the same computer to allocate memory all at the same time and do it in a way that you can actually get speedups, right? And there's fundamentally a lot of trade-offs here. But so yeah, there's that kind of that space of like how do you allocate stuff in parallel? That's even turns out a difficult challenge, right? But in a lot of these kind of lower level libraries for say fast allocation in programming languages like C and C++ and these sorts of things, memory management is still explicit. It's still like
Right.
you say when you allocate something, you also say when you deallocate something, right? And you have to be extremely careful about manipulating that, right? Versus in this kind of parallel functional programming world that a lot of the work that I've been doing, memory management is implicit, like so much more so than what people are normally familiar with. Like even in a language like Java, memory
Yeah.
management is still half explicit because you still have to be explicit about when you allocate something,
Hmm.
but you don't have to say when you deallocate something in Java,
Sure. Sure.
right? Garbage collector handles that for you. But you do have to say new object, right? New
Right.
array. You have to give me a new thing. And that memory, like, so you're thinking about allocation explicitly, and you're thinking about like objects in memory pointing to each other, right? Explicitly, right? Versus in a functional language, this is usually abstracted out of the language, right? Or it's encouraged to not think carefully
Yeah, I
about it.
think most functional programmers still think in terms of when I call this function,
Right.
it will instantiate this struct or whatever, and it'll return me like something that's already allocated. But what you're saying is that, in a functional language, you can even extract away when that thing is allocated, or maybe it gets optimized away and never gets allocated at all. Is that
Yeah,
what you're sort of getting at?
absolutely. I mean, I can give you a great example of this, which is that if you have um, a piece of like pure, like immutable data, right? So like imagine I have like a list storing tuples of stuff. I don't know. So like a
Right.
list that stores like tuples of integers and strings or something. Question for you. If I create a list of size 100, how many distinct things get allocated? This is
Hmm.
not something
Right.
which the semantics of the language necessarily like dictates,
Right.
right? The language doesn't say, oh, there have to be exactly 100 distinct things in memory with 100 pointers pointing to each other, or maybe even those tuples are separately allocated. So then you're going to have like 200 distinct things in memory or something, right?
Right.
Um,
Right. You can't really say things about the memory at that point,
right,
like in a
right,
functional programming language.
yeah. But you can say some things, right? Like, for example, in the language that we're working in, it has a strict evaluation model. So that means that you know that things are at least going to happen in order.
Right.
You know that like if you call a function and then you say do this thing, like you know that you first what happens is the function call happens and then the thing happens, right?
Yeah, Matt in the chat was talking about
Right.
laziness, like where this gets even more complicated.
Exactly. Yeah.
Right.
So okay, so that's at least one thing that we can say about it. And then you can go a step further because you know that you're working with a particular language implementation, right? In many situations, you know which language implementation you're working with, right? And this allows you to get more insight into the performance of your program. Because, for example, if we're with our compiler, I can tell you for sure, like, oh, these things are definitely allocated on the heap, and oh, these things are definitely not allocated on the heap. And then these things the compiler gets to choose. Like I can
Right.
tell you something about like what the um, memory model, if you will, for that implementation is. And functional programming tends to encourage people to not worry about those details. The advantage of this is that when the details don't matter, everything is much easier.
Right.
Like you
Right.
can just like write at a super high level of abstraction. Like you can easily create domain specific languages embedded inside of a functional programming language that like make it easy to do all sorts of tasks, right? Without thinking carefully about like how they're compiled, how they're optimized, all of this, right?
Right. So for people in chat that may not know it, domain-specific language is where you make some particular small little language for a particular domain or task. So an example of this would be like, I don't know, a lot of Python libraries like NumPy or Pandas are sort of embed a little domain-specific language for like dealing with data or doing specific sorts of tasks. You can think of them as a library or a language, but they once they start doing crazy stuff in Python and like have specialized syntax and things like these, they really are starting to describe a language. And Ryan says AutoCAD has its own DSL as well. So yeah, we're starting to get into this discussion of like why functional programming, why parallel functional programming, and what the advantages of this sort of way of thinking are. Maybe we should expand a bit on that.
Yeah, I think actually, well, one perhaps inciting question for this could be, let's say you're someone who's mostly written code in Python or something, right? So what is the difference in experience of first thinking about functional programming languages, thinking about and then sort of thinking about parallel programming languages and then combining those two together and building a functional programming language and the sort of mental model you work with, right? Because Python occupies this interesting space where you can mix a lot of different paradigms together. And people do recommend certain kinds of functional paradigms, even in Python, even though they might not call that functional necessarily. I think we should maybe go at it this way and try to sort of explain to people what's going on under the hood. Like, what is the true philosophy of like a functional programmer, and then build up to a parallel functional programming language.
Sure. Yeah. Yeah. So you mean like as a programmer, right?
Yeah, as a programmer. Yeah.
Good. Like approaching programming. Good. Yeah. So I mean, functional programming, there is no one definition of what it is. Everybody has their own interpretation on what functional programming is, just in the same way that everybody has their own interpretation on what object-oriented programming is, right? But I think there is some sort of like unified general mindset when it comes to functional programming, which is kind of hint, in the name. It's thinking about functions and like mathematical functions, like what you learn in school, in like elementary school and middle school and high school. You learn about like, oh, if I have a thing, I can add 2 to that thing, or like I can have a thing and I can multiply that thing by 2, right? And now that like general thought of like a procedure that where you can take a thing and do something to it and get a new thing. Let's like put that in a box, right?
Right.
Not worry about how it works, right? But I can feed things out and I can feed things in and I can take things out, right? And now that's what we call a function, right? And like, thinking about writing programs as just a bunch of functions that compose together, right? Now I should like be clear about terminology here. The word function, right, means many things in the world of programming. Okay.
Right.
But from a functional programmer's perspective, a function is a mathematical function, or hopefully, like that's kind of the goal is like, let's think about these, if we can, if it's possible, let's think about these things in terms of mathematical functions, where you're thinking about like this input goes to that output and this input goes to that output. And if I run it on Tuesday and if I run it on Friday, it always does the same thing, like if the box never changes its behavior, I can put the box anywhere I want and it still does the same thing.
Yeah, it doesn't affect the outside world if like it doesn't mutate its arguments or mutate some other place or any of that sort of thing.
Exactly. Yeah.
Right. And this is sort of the so-called pure functional programming model of thinking about. Yeah.
When people say pure, like usually what they mean is they're like every function can be interpreted as a mathematical function.
Yep.
I think the really interesting thing here is that there's like a big divide between functional programming and other types of programming. But a lot of people don't realize that, you can pick when you're programming in a functional style, like in a different language, or when you're using a programming language that restricts you to functional programming. Or you can even have a programming language that knows when you're in the functional fragment or when you're not in the functional fragment, or even does some data analysis for what's immutable. And like lots of your work exploits this sort of, we can analyze it or have types that tell us what's immutable and that sort of thing to sort of mix these two worlds together and get some benefits of both.
Exactly. There's a huge range of options here in terms of what the language guarantees for you. But going beyond that, like a discipline in terms of programming that can guarantee certain things, even if there is no like compiler that necessarily is going to check it for you, you can still be guaranteed of it just by adhering to that discipline, right? I think nowadays, like I think of functional programming as a technique more so than as a language paradigm.
Exactly, yeah.
And I think it's very useful as a technique, um, as long as like it's something which is actually feasible to do in a programming language. I mean, in some languages it's just not really like it's hard.
Yeah, they're sort of like when you describe when you start thinking about things as pure functions, there's this like detachment from the machine that you have to have in your way of thinking, right? Like you're not thinking about necessarily allocations anymore. You're not thinking about maybe even the kinds of resources you're using. You're just thinking about functions that take in things and produce other things. And so I think one challenge that people often find, and some of the questions people have already started asking, even about parallelism in the chat, is really reconciling this it's not a problem, it's a trade-off with functional programming, which is you detach yourself from the machine, but at the end of the day you might still want guarantees on your programs, you might still want performance for your programs, you might still want sort of specific workload characteristics, latency guarantees or something like that. And so like I think one thing like in the wild people struggle with when sort of just talking about purely functional programming models is, well, at the end of the day you're running them on machines and you have to somehow get guarantees, and you have to go to your manager and say, okay, I wrote this program in this weird way, but don't worry about it, it's more maintainable in the future, and also it gives you the guarantees that you wanted, and guarantees being different from just type safety, which is something functional programming also touches upon a lot. So what do you have thoughts on this? And I think like the parallelism question, we'll get into it afterwards.
Absolutely. Yeah, yeah. So a big aspect of our work, I think, the work that I've been doing and the work I've been doing with my collaborators is about addressing this exact question. How do you take, like, in some sense, I don't even, so maybe we can even abstract away from functional programming for a moment. Let's just think about high level programming, right?
Yeah.
Whatever the high levelness be, like the high levelness is I'm disconnected from the machine, right? The machine is like 30 compiler passes away from me,
Right.
or it's 100 compiler passes away from me or something, right? And how do you guarantee performance properties in that setting, right? So that's something that I think we've been trying to address in our research. The approach that we take to this question is to think about abstract cost models rather than hardware cost models, right? So if I have some way of looking at a high level program and reasoning about how it will perform, and then I rely on the compiler to adhere to that model, right? Like the compiler essentially is handing me a contract that says, I promise I will guarantee that if you do this, it'll perform like this. And if you do this, then it'll perform like this, right? So it's thinking about cost at the level of semantics for a programming language, just as you normally think about behavior at the level of semantics for a programming language, right? And it's a challenging problem. It's really difficult. Right?
Yeah, I think it's really challenging, especially when you start to consider space and space complexity, or time complexity, or like preserving complexities, or that sort of things. Or if you can give hints to the compiler, now you can do all sorts of new things.
Absolutely.
There's a huge space here, yeah.
Yeah. So I think even just the most basic things, in terms of like, for example, I mentioned this idea of like a strict cost model, or sorry, a strict evaluation model, where you know that like the things happen in the order that you wrote them, like in your program, right? This is like already heading in the direction of having a high level cost model for the program, right?
Right.
Because if I can reason about the cost of whatever the primitives in the language are, and I have a way of composing those costs by reasoning about control flow or something like this, right? Well, now I can start to think about like, okay, how many times do I go around this loop? And every time I go around the loop, I do one allocation of this sort of object and whatever. And so now you can start to count these sorts of measurements that have real impact on performance. I think the holy grail for this, right, would be for all of this to happen automatically.
Yeah, I think the automatic
holy grail is a bit
complexity
strong.
inference work is really interesting, but not something I have thought deeply about yet. It seems very tough.
Exactly. Yeah. I mean,
Yeah.
fundamentally, the challenge here is the halting problem, of course.
Right.
Like you can't. This is something. So for people who are viewing who are not familiar, there are fundamental problems that are actually known to be unsolvable. Unsolvable in the sense of like the universe does not allow it. And one of them is called the halting problem, and the halting problem says that you can't write a program that given arbitrary input, where the input is a different program. So imagine you're writing a program which is analyzing a program. Okay. So you're writing a program that it's allowed to look at the source code of another program. And then it has to make a choice. Like, yes, definitely this program will halt after some number of steps, or maybe this program will run forever. Like, those are the two answers that you're trying to figure out. It turns out that this is impossible. It's like known to be actually the universe does not allow you to write this program. It's because it turns out if you're capable of writing this program, then you can create paradoxes. Like, you can ask the program you can ask the program about itself, and then like you end up in an infinite loop that it doesn't, where like
if you run into contradictions.
If it stops, then it will say it loops forever. And like,
right.
Okay, so anyway, but what's interesting is that classic problem says that, okay, you can't solve this kind of thing in general. Like, if you wanted to know how long does my program take to run, right? This is not something that you can definitely say for sure in general, right? That doesn't mean you can't say for sure in specific cases, right? You actually can say for sure in specific cases what the behavior is going to be, right?
Yeah.
You can look at, for example, you can look at a loop and see that you have an index I that's going between 0 and n, and you can see in the source code of the loop, every time around the loop, I goes up by 1, right?
Yeah, and there's this argument
exactly n iterations, right? Like, who cares about the halting problem? We've solved this particular problem. No problem.
There's this argument that like humans wrote a program and they were able to reason about it, so it must be some small subset of all the possible programs and maybe easier to reason about. Like, if the human was able to do it, maybe the computer can do it.
Right. Exactly.
Yeah.
The only thing the halting problem says is there exists a bad program somewhere that we can't analyze. That's the only thing it says. Right? But actually, most cases you can analyze. And so a lot of people have worked on static analysis of cost, where without even running the program, you can get a good estimate on how long it'll take to run, or you can get a good estimate on how much space it'll consume when it runs. Right. And I think this is not something that I personally have worked on in terms of like research topics, but it's definitely like a big area, and it's like very exciting area. But there's a lot of limitations to it. I mean, it's a very difficult, like, usually what it can give you is like some sort of reasonable upper bound, but it maybe can't give you something very precise in many cases.
Right. Yeah. So this is an interesting rabbit hole, but I do want to.
Yeah, it's time to pop back up.
But just to summarize, I think you've hit a couple of very interesting points that often show up when you start thinking about languages and design. Was like, saying that something is hard to solve or impossible to solve or is sort of Turing complete is the most uninteresting thing you can say about a general programming language. Because yes, of course, most interesting properties of programs are extremely hard to prove or impossible to prove, right? So a trade-off that we often think about as language designers or people building tools for languages is, yes, we can't solve the general problem, but how can we change the language and change the tooling and sort of make the user give us hints and information such that we can solve the problem in a more pragmatic way, right? Like, being a language designer is fundamentally this, like, you have to somehow not succumb to the painful line of thinking. It was like, oh, I can't solve this in the general case, therefore it's not worth doing. It's worth doing, but it's a trade-off. It's an extremely complex trade-off space, and so that's something you explored. You mentioned this word composition, and now I want to get back to it because I think that this is sort of a thing that we talk about often in functional programming. So, how about you use that as a lens to describe what TheForkJoin is? So this is the curtain reveal. Like, the reason this show is called TheForkJoin and Sam is the first guest is because Sam has worked and thought deeply about the TheForkJoin programming model, and so you'll tell us what TheForkJoin is. And looking at it through the lens of functional programming. And I think then some people have already asked, how do you compare this to things like Java's TheForkJoin pool and existing implementations in imperative languages? So
excellent. Yeah.
Let's start like a small mini lecture on this, maybe.
Sure. Yeah. Good. So like, maybe we can do it from the lens of functional programming, and then we'll come back to kind of generalizing it to other contexts. But in functional programming, we often think about when the mental process of saying do A and then do B is usually translates into call a function and then feed the output of that function into another function, right? So you kind of like do F and then do G on the output of F and then do H on the output of G, and blah 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 blah. Okay.
Yeah. Yeah.
So this is what we call sequential composition. Okay, so by sequential, what we mean is, this and then that. So this kind of thought of like things happening in a sequence, right? And what's nice about functional programming is that if we think about these things as black boxes, and the black boxes are not allowed to interact with the world, right? I can do this and then do that, right? But what if I'm in a situation where I'm not feeding the output of one into the other, right? Like if I'm feeding the output of the first thing into the input of the second thing, well then like you need to do them one after each other, right?
It's a constraint, right? Yeah.
It's a constraint, exactly. But what if you're trying to do two things on the same input, right? So what if I have a list of email addresses and I want to apply a template that writes an email for me for every email address or whatever, right? They don't need to. Yeah. You can do all these things at the same time. Okay, I can. The function is a black box that you feed it an email address, and out the other side comes an email that you've written now for that address or whatever. Okay, but if I have 100 email addresses, I can do 100 of these tasks all at the same time, right? So this is what we call parallel composition, and it's in the absence of these dependencies. If you don't have a dependence that this has to happen after that, right? Well, then you can do them at the same time. Okay,
and so to really like hammer the point home, the question was asked contrasting to like fork join in Java. Well, if you were going to use it in Java, you would have to guarantee that these things can be run in parallel, that it's like a functional programming program. But if you're in a language that is restricted to be functional or somehow proves by itself that your functions are pure, then you can do this safely without having to like think about it or prove to yourself that it'll be like correct in any order. So that's what Sam is sort of getting at, right?
So we should talk about though like what these words fork and join mean.
Yes, we should.
Yeah.
Yeah. Okay. So in sequential composition, right, one thing after another, this can all kind of happen like on the same processor or like on the same thread or like by the same computer, like kind of all in the same place, right? But when you're trying to do two things at the same time, okay, they can't happen at the same time, but also in the same place.
Right.
Right. So this is where typically the programming model has some sort of notion of tasks, where a task is like this thing that you can like put on a machine and say, hey, run this task for me, right? Or you can put it on a processor in your machine and you can say like, run this thing for me, right? And now fork and join refer to how these tasks interact with each other. Okay, so what you can have is a task that says, hey, I have an opportunity to do two things at the same time. Okay, so what it'll do is it'll fork. And fork means take one task and split it into two tasks, right? And then you can do these two things at the same time because you can send them to two different machines or you can send them to two different processors and ask two different processors to execute those two tasks at the same time. Now later, you might need to like assemble all of those results together, right? Like I have a bunch of different things that have all finished in parallel, and now I want to accumulate everything that I've learned from finishing those tasks. This is what we call a join. So the join just means that you have two things that were running independently of each other, but now once again you have a dependence. They come back together, and you once again are kind of back in the sequential world. Okay, but here's something really cool. I can say, oh, hey, here's an opportunity to do two things in parallel. So I can fork, right, into two things. Now, each one of those independently might say, hey, I have an opportunity to do something in parallel. And like, they can fork, right? So these things can you can create as much parallelism as you can find. That could be something which is dependent on the input, right? It could be something which is determined by randomness. It could be like, who knows? Why?
So like your email example is like every time you get a request to templatize an email address or something, you just fork and you go from there. And that's sort of representative parallelism in that workload that you go in. But so I think the nice thing about ForkJoin is it's a very clean, beautiful model, right? Like it's an expression of absence of dependence and dependence dependence on computation or something like that, right? Like fork is like you saying, I promise there's no dependence between these things, and therefore you can run them separately. And then join is saying, I want both of those computations now, and so please create a sort of sequential dependence on them, and then continue the computation.
Exactly.
But I was talking about this like machine independence, right? So bringing this back to machines, well, of course, our machines don't have that much available parallelism, right? Like even if let's think about a very simple machine where there are no threads, there's no like magical SMT or anything going on. The only thing that happens is we have physical cores that can run computations independently. We're not even thinking about caching, which I know like your work, of course, has to deal with, and that's the cool part about it. So let's say we have 16 cores, or let's say we have 2 cores, but our fork join workload is saying there's 16 possible parallel things. How does a fork join compiler deal with this reality that yes, the model is sort of abstract in this way, but the machines are physical and real and have constraints?
Absolutely. Yeah. So the typical solution is you have a scheduler which runs dynamically alongside your program and puts those tasks onto processors or onto different computers or machines or something in order to run them, right? Now, at the level of a typical low-level programming model in C or something like that, the mechanism you have available to you is what people call an operating system thread, right? Or specifically in C, it's like they call it a P thread. Okay.
Yep.
So this thing is basically a full process on your machine, and it is extremely heavyweight.
Yeah.
The amount of time it takes to like generate one of those things, to like create it in memory, is significant. I mean, let's be real, it's fast. Like as far as like human scale things go, like we're talking about microseconds here, right? But if you compare that against what happens exactly, like adding 2 numbers in hardware, okay, now you're on the scale of like nanoseconds, right? This is like many orders of magnitude difference in scale, right? Okay, so we have these, so we like to call them heavyweight threads or coarse threads.
Yeah.
Those are the things that typically your operating system, like Linux or Mac or Windows or whatever, makes available to you and says, hey, you can generate these things and I'll put them on different cores for you, okay? All right, if it turns out that if you try to write a fork join program where every time you fork, you generate one of these OS threads, good luck. I mean, it's not going to perform well, because every time you fork, you're adding like an additional millisecond, or who knows how long it takes, depends on the machine, depends on the operating system, but you're adding
depends on what you're forking for.
Yeah.
I guess, right? One clarification there is that if you're forking for like really heavyweight tasks, which is, I guess, why we have access to B threads in the first place, then it won't perform too poorly. But it's in the word. You said they're called coarse grained threads, or you call them coarse grained threads, and that's precisely it. It's the coarseness of the workload that we were talking about. But
exactly.
Please go ahead. Yeah.
So what we need for a like high-level parallel programming model typically is fine-grained parallelism, where we need to be able to say, create a task, right? But the cost of creating the task needs to be small enough that you can create as many as you need, right? If I have a machine that has 4 processors on it, I don't need to restrict myself to only 4 tasks. I'll create 1,000,000 tasks, right? And now I'll let a scheduler figure out how to schedule those tasks onto the machine, right? So typically what we have is it's this magical thing, the scheduler, right? Okay. It turns out it's not terribly difficult to write one of these things. All right. Like
not terribly easy or hard, you said?
Not terribly hard. Now, take that with a grain of salt, because like for my expertise, like I'm like, oh yeah, it's not hard. Like I've done it before. But like, okay, yeah, it's probably tricky, right? But like it's not some mysterious piece of incredibly magical software, right? The source code of like a decent scheduler for like the kind of parallel programming languages that we're talking about today, it's not that much.
Yeah.
It's like 200 lines of code or something. Wow. It's not bad.
Sure.
And these things are capable of scheduling millions of tasks. We call them lightweight tasks. Typically, they're small descriptions in memory that'll say like, it's basically the equivalent of a function closure. And now I know I'm introducing a new term here, right? But like, okay, to give some context for people, like if you want to execute a function, if you want to call a function in a programming language, you need to be able to say like, oh, well, like here's the name of the function that I'm calling, and here's the arguments that I'm going to pass to it. Like the the memory addresses of the arguments that you're going to pass to it and these sorts of things, right? Well, what if you just wrote down that stuff in memory? So I know the name of the function and I know like what arguments I'm passing it. Let's write that down in memory and let's think of that as my description of a task, right? That's very small, actually. It's like 100 bytes or something. I don't know, 500 bytes, let's say at most, right? But it's pretty small.
You're sort of gonna have that already. Like maybe it was in registers, but like it was there already if you were running sequentially.
Exactly, it's there anyway. So now what I can say is I'm going to take that little package and I'm going to hand it off to a scheduler, and the scheduler is going to figure out when it wants to run it and who is going to run it. Which processor, right? And it does this in a clever way where you have this distributed task queue that everybody can kind of pull and pop from and push and pop from, and this kind of stuff. And it's all very scalable and fancy, whatever. But anyway, that's the actual mechanism that we use to schedule millions of tasks, let's say, onto a constrained number of resources. Yeah. And do so efficiently. So, doing so efficiently is a huge part of this story, right? Yeah.
Right. There's sort of, to distill your answer, there's like fundamentally the problem of taking logical computations and mapping them on parallel physical resources requires something called a scheduler, right? The OS has one, language runtimes like Maple have one. Well, I guess the language is not Maple, the language, well, okay.
Oh, we can call it Maple, that's fine.
We'll call it
MPL,
Maple.
yeah.
Right. MPL, yeah, right? And like, so schedulers are the key thing that make this abstraction work. One of the things that you mentioned is this ability to schedule lightweight, basically parallel tasks. And a programming language that immediately comes to mind that has this tagline is, of course, Go, which again has this extremely simple way of creating parallel tasks. You just have like a Go keyword in front of your function, and now it will run in parallel for some definition of parallel. So let's dig into what Go is and what it tries to do and how that model differs with something like MPL. Or if it's similar.
Yeah, it's great. Like a lot of people are probably familiar with Go. And so essentially what Go gives to you is a really easy way of working in an efficient way. And it has a scheduler built in. So the Go runtime system has a scheduler built in, which manages these little tasks for you. And you can create, millions of these tasks, no problem. And Go will figure out how to schedule them onto different cores for you, right? Now, here's something Go won't do, okay, is try to figure out if this is safe to do.
Right.
Hey, right? So describe that word. Sorry, Oliver, you're saying.
Yeah, exactly. I was also going to dig into like, what does safe mean?
Yeah.
What is safe?
Good. So let's say that the three of us are at the whiteboard and we're working on something together, right? And we figure out like, oh, hey, like there's this little thing that we all need to go do. So like, let's all go work on our own for a minute, right? And figure out this thing, and then we'll come back and we'll like put together what we figured out and on the board or whatever. Okay. So I'm like, all right, I'm going to work on the board right here, right? And I start writing on the board. And meanwhile, Oliver is like, okay, I'm going to start working on the board also. So he starts writing on the board. But then I start like invading Oliver's space.
How dare you?
Right? I erase some of the stuff that he's written and I write on top of it because I'm working on something hard and I need the space, And now Oliver comes back and somehow Oliver doesn't notice, right, that I've erased. Like all I've done is like he wrote, 1 + 1 = 2, and I was like, I need this space, so I'm going to replace that 1 with a 3.
It's like a game of crossword where different people are just like overriding each other's clues or something like that.
Exactly.
Right?
Yeah, we're all trying to like interact with the same resource, and we're not trying to coordinate it at all, right? And now what we have is what typically is called a data race. Okay, so this is where two different independently, seemingly independent computations are interacting with the same resource, and they're making destructive changes to that resource. So in this case, like we're both writing on the whiteboard at the same time, and we're overwriting each other. We're erasing each other's stuff and overwriting it. Okay?
So it's not just destructive changes, it's destructive changes that are visible to the other person and sort of affect them as well somehow.
Exactly, yeah. And we use the term effect generally to describe this kind of phenomenon, because you can think about a black box, right? As I feed it some input and I get some output. Maybe there's one more aspect to this, which is the effect that the black box has on its environment. right? So
Right.
now
Right.
if I am the little black box that's like computing something, but the way in which I'm computing it is by writing on the whiteboard, right? Well, now I have an
Right.
effect on my environment. And if
Right.
these effects don't interact well, then it's not
Yeah.
safe to do these things at the same time.
Right. And so
So
safety is really a property about resource exclusion or like principal use of resources in a way that we don't clobber each other's computations, we don't clobber each other's sort of information, and we can all sort of proceed doing the thing that we wanted to do independently in our parallel threads or something like that.
exactly, yeah. And
Right.
functional programming, in some sense, is just a technique for controlling this. I mean,
Right.
it is much more than that, of course, as well. Like there's all these really cool things you can do with functional programming once you're like really deep into that space. But on a
Right.
first cut, like what is functional programming? It's a programming methodology and a discipline that like lets you control where the effects are. And
Right.
if I can if I can look at a black box and say for sure it's not interacting with its environment, right? Like
Yeah.
if it needs a whiteboard, it has its own whiteboard or something, right? You know, like
Right.
and it's not sharing
Right.
it with anybody. Then you
Yeah.
know that these things are safe to actually run at the same time. I can run them at the same time and not be worried at all about what the impact is going to be.
I really like the definition that you just gave about functional programming, which is a way to control effects, right? I think a first cut for people thinking about functional programming is eliminate effects. That's not the goal of functional programming. It's a principled way of thinking about effects. And so like one way that occurs for me is like in functional programming languages, your signatures will often tell you what resources you're interacting with and how. And that's a big rabbit hole, so we're not going to really get into it. But languages that are fundamentally imperative, like Rust, have really been inspired with that kind of philosophy, and they really sort of express their capabilities and requirements in their sort of signatures. And so I think like I really like the crisp definition of functional programming that you give. I think like
Yeah.
controlling effects in a
You
way
know,
so you can give guarantee.
and at a certain point, you have to start asking the question: is Rust a functional programming language?
I was about to say Rust is my favorite functional programming language.
It's probably one of
Right.
as far as functional programming languages go. I think it's carved a niche for itself in the
Yes.
functional programming space.
Right.
I'm willing to
And
say
this
it's a functional programming language personally.
Yeah,
Yeah, and
yeah.
this is why we'll be on Hacker News tomorrow with like a title, three nerds trying to ruin our favorite program. It's good. But yeah, so I mean, of course, it has deep roots to all that stuff.
Mhm.
Um, Oliver, you had a question in the middle. I don't know if it got cut off while I was speaking.
I'm not sure. I think I forgot what I was gonna
Okay.
say.
Yeah.
Cool. We could do like a 5 minute break if people need to use bathroom or go get water or something. And I
Yeah,
think
or like an open question time. I think it now would be good time for some audience interaction
Yeah.
or
So
deeper rabbit hole type questions. That
and
sort
it
of
looks
thing.
like we had some
yeah.
questions already about about writing fork join programming and stuff. So I'd be happy to answer some of these. So yeah, so one of the questions here was what's the advantage of writing a parallel programming language over doing fork join as a library or a DSL, say for example in Java. Yeah. So okay, so this I guess is related to what we were just talking about, with the example with Go. Um, I think the main difference is just this issue of controlling effects. If you have a programming language where control over effects is explicit in the language itself, typically it's much easier to write correct parallel programs. If you don't have explicit control over effects, it's still possible, of course, to write correct parallel programs. But I think one of the things that becomes challenging, yeah, so maybe I should clarify actually. Like in some sense, it's easy to write parallel programs if you know everything about how the program works, right? Like all the details of how all the functions are implemented, and like maybe you wrote everything yourself and you have it all in your head. It's not big enough, so big that it escapes your own head, right? You can think about things carefully and like, oh yeah, these things are definitely independent. They're not interacting with the same whiteboard at the same time, and so they can run at the same time, right? But what if Oliver writes some code and I write some code, and we're like, oh yeah, we could do these two things at the same time, how do you check to make sure that really is the case, that these two things are safe to run? at the same time. So in some sense, there's like this additional problem of like modularity and like being able to confidently take a piece of code that you don't know how it works and know that it's safe to run it at the same time as a different piece of code, right?
But Sam, we've talked a lot about safety, and I think you may be underselling a big point, which is your whole research. Like, making a parallel functional programming language with TheForkJoin instead of as a Java library allows you to do like all sorts of crazy cool stuff involving like automatic memory management and making the garbage collector faster and these sorts of things. Maybe now is a good time to chat a little bit about um, like your research and the bleeding edge of like what may be possible if you have these guarantees instead of being in Java land.
Definitely. Yeah. Yeah, this is a question that I think we've been asking ourselves, like on the work that we've been doing, me and my collaborators, like what is it that we're really using, right, in our work? What's the thing that.
Exactly, the minimum
The,
viable like platform.
exactly. I think the thing that we're really taking advantage of is static knowledge of immutable versus mutable data. And by static, what I mean is without running the program. So like at compile time, the compiler knows which things are immutable and which things are mutable, right? And okay, and there's more also that we're taking advantage of. But like in terms of, okay, some context here. So what have I been working on for my PhD thesis, and like what am I still working on to some extent? So we've been working on how to take a parallel functional programming language and actually make it fast. And half of that story is, okay, you just need a good compiler that is good at optimizing code and generating fast code. Okay. But the other half of the story is you need a good memory management system that's capable of allocating and reclaiming memory efficiently, scalably, in parallel. Okay. So what I ended up doing for my PhD thesis was designing a parallel garbage collector. And this parallel garbage collector, what we're trying to do is take advantage of guarantees that we get from the programming language or from the programming model, right? And we're trying to take advantage of those guarantees to do things more efficiently. Okay. So one example of a guarantee that we get from the programming language is a distinction where this memory is definitely mutable and this memory is immutable and will never change, right? This is something which is extremely useful for designing a garbage collector, because in a garbage collector, I should give some context on what garbage collection is, I guess. What is garbage collection? Okay, so in your favorite low-level programming language, like C, you have to say allocate something, and later you have to say deallocate something. Okay, and you have to explicitly tell like the language, if you'd like. If you imagine as a dialogue between you and the programming language, you have to explicitly tell the programming language, I am now done with this piece of data, and you're free to reuse that memory for some other purpose. Okay. This is very error prone. If you're not careful, you might tell it that you're done with something even though you're not done with it yet. And now it might start using that memory for something else. And now your memory just looks like garbage and your program crashes, or actually a crash is the best case scenario. If it crashes, great, but how about it like does something really bad, right? It keeps running silently, even though something has gone bad, right? And it like, I don't know, turns on your car and starts driving your car down the road or something.
Puts money in someone's bank account or something.
Yeah, it steals all your money from you by accident because you also put the passwords, right? Okay, so because of this problem, we would like to have a high-level approach that avoids the problem entirely, right? So we have automatic memory management, right? Which famously is in languages like Java, okay, but also is in, like all sorts of other programming languages, and functional languages are a good example. And with automatic memory management, you have a garbage collector, and the garbage collector will figure out which pieces of memory you're not using anymore, and it will deallocate them. But it'll do this automatically in the background and in a guaranteed safe way, so that it's never going to throw away something that you're still using. Okay.
Yeah, and I think a lot of people think of the garbage collector as something magical, but really it's just a really tough graph problem and a big chunk of code that you write to solve this graph problem, to like move stuff around and try and like reduce the memory usage over time by like getting rid of stuff it proves you'll never use again in your code.
Yeah. And it's an interesting graph. So let's think about it as a graph problem. So what you have is objects in memory. So by the way, I'm using the term object not in the sense of object-oriented programming, but as like a unit of memory allocation. Okay, so like an object is like a single array, or it's like a single tuple, or like something stored in memory. Okay, so you have these objects. Those are kind of like the vertices of a graph. And those objects have pointers to other objects. Like you can store in a list a pointer to the things that are the elements of the list, for example.
Right, so pointer, we just used that word. Not like a C pointer where you have access to the pointer, but like an internal pointer, like if you made a reference to something in a functional programming language and just used that thing, that would be like a pointer from the garbage collector's point of view.
Exactly.
Great. And continue.
Yeah, so at the high level, you maybe don't have the notion of a pointer in your programming language. But from the perspective of the garbage collector, what the garbage collector sees is objects and pointers. And what the garbage collector does is it walks through this graph of memory. So we call it the memory graph, okay? But these, you start at an object, you follow the pointers that come out of that object, you see where they go. And the garbage collector just conservatively assumes anything that's reachable by following these pointers, the program might use. So it's just going to say, I'm going to keep those things around, right? But anything that is not reachable by following these pointers, right? Because maybe you've changed one of the pointers. So like maybe you had like A points to B, but then you changed the pointer. So now A points at C. Well, now this thing is no longer reachable anymore. And the garbage collector eventually will come through and it'll deallocate it. It'll make that space available for a different purpose. So I've already kind of gotten into why this is a tricky, in that little example, like there's a trickiness here, which is that the garbage collector is sitting alongside your program, and your program is changing things. It's coming in and it's allocating new objects, and it's changing these pointers and so that they point somewhere else, and moving things around. This is part of the reason why it's so difficult to write a good garbage collector, is that the program is interfering. The program is changing things, right? Okay, so now let's come back to, I was talking earlier about mutable versus immutable. Why does this make memory management easier? Well, it's a guarantee. It's a contract that says the program is not going to change certain things, right?
Yeah, you sort of don't have to look at it again, or like don't have to re-explore certain things because you know it won't be changed, that sort of thing.
Exactly. Yeah. Or there's cool tricks you can do. Like if I start at an immutable object and I start walking through memory, and everything that I see is immutable. So I'm following the pointers, and it points to another immutable thing, and that points to another immutable thing, you know. Well, I never need to walk that space again, right? I've walked it once. I've figured out what's reachable from it, right? Maybe I can design my garbage collector in a clever way that I never have to trace those pointers ever again, because I know they'll never change. If I trace them again, the result will be exactly the same. I'll figure out it was exactly the same chain of objects that were all pointed at each other, right? There are tricks like this that you can take advantage of in order to design a really efficient garbage collector. And that's definitely one of the things that we're taking advantage of in our work. We offer a high-level cost model that lets you reason about the cost of automatic memory management for your program. And part of that cost model is actually being able to distinguish between immutable and mutable objects. Kind of at a very, 10,000-foot summary, immutable things are cheap and mutable things are expensive.
And just to give the audience a sense for like how hard this problem is and how recently we're getting our hands on it, Sam, as far as I can tell, only considered like everything in the program as being immutable for a long time, and like came out with some papers on like just garbage collection for completely functional languages. And only recently we've decided that like, oh, some of these tricks can still apply if you like restrict the mutation, or like even if you're mutating everywhere, we still can get some benefit from some of your ideas in the garbage collector. So that's really really exciting and interesting to me that like we can lift it up to the general case. Yeah.
Yeah, and it comes back actually earlier we were talking about this problem of like, oh, maybe it's unsolvable in general, right? But you can still solve it if you restrict your attention. You like can, if you can describe the nuance and you can describe what is the interesting property that if I focus on that property, I can make guarantees, I can provide guarantees, right? So if you say, oh, the program might mutate memory and therefore all bets are off, there's nothing I can do, right? This is like, that's a first cut that you can make, right? But there's more nuance that we can extract, right? We can say, okay, in the situations where it mutates memory, maybe I'll fall back on using an expensive technique in order to handle that in the garbage collector, let's say, right? But in the cases where it's not mutating memory, I can use like these cool tricks because I know it's immutable, right? And you can get the best of both worlds.
Yeah, pretty neat.
Yeah. So there is this like deep underlying fact about mutability that you can use to get these kinds of nice guarantees. I'm curious, what do you think about like taking some of these ideas and applying it to something like Rust, which again allows you to specify mutability and immutability, both using the concept of ownership, but also in the send and sync traits that it implements.
Absolutely. Yeah. Okay. So Rust is an interesting programming language in this space because I'll make a hot take right now. Rust has garbage collection. Because what it has is a combination of static garbage collection and dynamic garbage collection. Statically, it figures out when it can deallocate things, and it inserts those deallocations into your program, right? Dynamically, it also does reference counting. And
in an opt-in manner.
Say again?
In an opt-in manner, as opposed to something like Swift, which does it by default.
Exactly. Yeah. So you like the types will make it clear where the reference counting is happening in a programming language like Rust. So like just by looking at the program statically, oh, there's going to be a reference count that gets figured out for this object. Oh, we should define what a reference count is. So what is a reference count? So it's a method of garbage collection where what you do is you keep track of how many pointers are pointing to an object. And when a pointer gets removed, you have a count, basically, like a mutable counter on each object, which is keeping track of how many references there are to that object. And when you create a new reference, you increment that counter. And when you remove a reference, you decrement that counter. And so when the counter goes to 0, that nothing is pointing at this object anymore. It's not reachable anymore, so you're free to deallocate it. And in languages that don't have super fancy runtime systems, reference counting is probably the most popular form of garbage collection that's typically implemented because it's possible to implement reference counting as a library. This is one of the reasons why it's so common in a lot of languages. But I think it's very helpful to think about it as garbage collection. There's a really cool paper about this, by the way. There's a paper called The Unifying Theory of Garbage Collection, which makes this very precise about how reference counting is actually a form of garbage collection. That actually, one of the things that it points out is that reference counting suffers from the same performance problems that garbage collection does. Reference counting traces the memory graph. It just happens to do so at a different time.
Right.
Garbage collection likes to periodically trace your memory graph in order to figure out, or tracing garbage collection, let's say, likes to periodically trace the memory graph in order to figure out what is still reachable. Whereas reference counting, you trace the memory graph as soon as things are no longer reachable. So at the moment something becomes garbage, you then trace everything that's reachable from it that is also garbage. Because what happens is you deallocate this thing that removes its outgoing pointers, which causes other reference counts to decrement, which causes you to trace those objects and deallocate them, and so on and so on and so on.
Right.
So, okay. So anyway, so coming back, so Rust. So Rust is this interesting programming language that has static memory management automatically, okay, where it deallocates memory automatically for you statically, but it also deallocates memory for you dynamically, and it does that by, at compile time, like marking which things need dynamic deallocation, right? Now, Rust in its current setup is going to mandate, right, that those things are reference counted. Like that's the mechanism by which those things are deallocated. Okay, but in principle, there's nothing stopping us from extending Rust with a tracing garbage collector, and perhaps giving that a different type if you'd like. But so you have a different type of object, which is like traced,
yeah.
in order to do automatic memory management. And I think this is possible. I mean, I'm sure somebody's looked into it. I don't know. I mean, people have tried to do this in other languages before.
Yeah, I feel like allowing the user of a language to pick their memory management strategy is very interesting. In Rust, you can write unsafe around all your code, and you're in C land. You can do whatever you want and manage your memory by yourself if you want to. If you don't write unsafe, it'll restrict you in the types to things where it can prove it just deallocates it at the end of like a function scope.
Yeah.
And
But crucially, it still doesn't.
yeah.
Sorry.
No, say what you were saying.
Yeah, but crucially, it doesn't give you a way to just like enable automatic garbage collection. You still need to put these RCs everywhere, and whenever you move between RC land and normal Rust type land, it's kind of painful and it's sort of it's challenging. But again, like yeah, there is a spectrum, and it's sort of it's interesting to think about how you can combine these things together in like a nice productive manner.
And Eli just sent us a link to garbage collection as a Rust library, which looks very interesting.
Right. I think actually
Cool. Yeah.
that's cool. I think there was a question by Matt here about deallocation. So the question reads, deallocation, or maybe the comment, deallocation and allocation are the sort of ultimate shared mutable state problem. And if we have a single global allocator responsible for all allocations in the program, this would be problematic for both efficiency and reasoning about performance, right? And so this is curious about, well, reacting to that comment. I think it's really getting to the point where like, when we think about these parallel programming languages, we think about the scheduler or the runtime, which includes both the scheduler and the garbage collector, right? And they sit in the middle and they are in charge of coordinating everything. And so one thing we have sort of discussed a little bit is about how coordination can be expensive. This is sort of a theme in parallel programming and distributed computing, sort of distributed computing, where like whenever you need to coordinate, you're going to pay some penalty for that. And so I think this is a good point that if we have a centralized runtime, what are the costs we're paying for that? And is there a way to think of our runtimes as more decentralized entities, build them in a more decentralized way, and get back some of those efficiency costs that we're paying for the centralization?
Yeah. The centralization aspect is fairly minimal, to be honest. Like it's centralized conceptually, but it's not centralized necessarily in terms of like performance contention, right? And by contention, what I mean is like different threads of your system or different tasks of your system competing for the same resource and having to wait for each other in order to use that resource. So if you think about like the memory of your program as a big shared resource, and you think about all of your threads and your tasks as competing for access to this resource, in some sense, okay, yeah, they are like competing for access, but also like it's not usually the case that there's much contention here. There's contention here if you're running out of memory, right? So like if I have 100 gigabytes of RAM on my computer, right? And right now I'm using 10 gigabytes, right? It's very easy to design an allocation system that has essentially no contention, right? But if I'm currently using 99 gigabytes out of my 100, or maybe I'm using 99.9999, whatever, I'm getting very close to the memory limit. Well, now I'm actually contending because there's only a tiny little bit of memory available, and everybody's going to try to use that memory, right?
Right. But okay, so let me push back on this a little bit, because so we've been working with a relatively simple model of the machines for explaining the concepts, right? But really, like a performant program on like a modern machine doesn't just think about main memory, which is the DRAM, right? It also needs to think about the cache hierarchy.
Uh-oh.
And the cache hierarchy is not 100 gigs, right? It's much, much smaller. And so this is where I think this is where the contention question really is trying to come to, which is like, okay, if you're evicting cache lines too often, or your scheduler is doing something silly to really affect the cache in a bad way, you're going to have really poor performance, right? And so I think that's a big question to think about and try to answer here.
Yeah, I think so. There's my take on like the cache efficiency sorts of things is that like if I'm designing a scheduler, there
Yeah.
are techniques that I can use in order to guarantee that the scheduler itself doesn't interfere with cache efficiency too much, right? It's a big can of worms in terms of there's tons of research that we would need to go dive into in order to really understand how to implement a scheduler that doesn't impact your cache efficiency too much. But like you can do it, right? So then that's something that you can embed in a programming language, right? And not expose to the user. I think the question becomes really interesting when you start to ask when does the user need to care about cache efficiency? Like when does the programmer need to care about cache efficiency? And for this, I think the correct solution is to make these kinds of costs explicit in the way that you reason about your programming, right? You when you're writing your program, you like one of the things that you're thinking about is cache efficiency, potentially. You don't always need to, right? In many cases,
Right.
you don't care about performance and you just don't worry about it, right? Right. But sometimes you do care about performance and you need a mechanism for being able to reason about it, right? And I think the only important thing is that if a programming language implementation has some impact on cache efficiency in a significant way, right? That's something that the programmer is capable of reasoning about in the cases where they need to, right? So I think sometimes there's this grand goal of like, oh, you need to implement it so that it doesn't have any impact on cache efficiency. I think this is not, it's too ambitious of a goal. It's like never going to happen.
You should back off and like provide mechanisms for how to reason about like what that impact will be.
Exactly. Yeah. If I can characterize like what are the performance characteristics of this programming language implementation, right? And expose that to the programmer, right? Well, now you can actually start to reason about performance as an aspect of the program that you're writing and not as something that's determined by like, some weird compiler choice and some weird like who knows and whatever.
And
So
on
I
like one machine, it runs faster than another because the compiler version's different or something.
Exactly. Yeah.
I yeah, I really like that answer because it is exactly what I think too in some ways. But it is somewhat the challenge I have with this answer is it is at odds with the goal of functional programming in the way we were talking about it earlier today,
Okay.
where it's sort of maybe you can tell me where I'm wrong about this, but here's one line of reasoning, which is that the idea with functional programming is you want to detach yourself from the machine. You want to specify these nice compositional structures and sort of tell them what they compute, not how they compute. And there's something magical sitting at the bottom that knows how to transform that description into a good computation, whatever that may be. But now we have come to a place where we've actually said, okay, like, yes, you can have high level descriptions, but at some point, if you really, really care about performance, we're going to have to expose it to you as a knob in the programming model or the compiler or something, and you have to be aware of it, right? I personally don't mind that too much. There was a question about user scalable languages very
Yeah, I
early
was
on.
actually going to
We
bring that
should,
up, but yeah,
right.
finish that first. Yeah.
And so maybe that's why it's not at odds. But like there is giving up of ground going on here, right? Like there's something we're saying about like, hey, we're going to give up on this pure programming model or this cleanup programming model. And one domain I want to point out to where I feel, okay, I'm not an expert in the domain, but where I feel that they have really managed to retain high level abstraction and performance is machine learning, right? When you talk to people building machine learning kernels, okay, if you're really, really pushing on the boundaries, you have to know about how like various tool chains work and how sort of PyTorch or TensorFlow is scheduling and compiling things. But at a very high level, they've really managed to give you this nice abstraction of staging computations and then levels of compilers that can target complex hardware like the TPU, right? And so maybe that is not necessary. Maybe one answer is you push you push yourself into domain specific languages. Maybe you do something like user scheduling. So this is a big question. So I'll give you space to answer this.
Yeah, so I think where you're going with this actually, and I think the user scheduling languages actually is kind of uh, a nice setting for kind of discussing how this can work, right? But
Right.
fun- so functional programming historically has been about like um, writing your programs in such a way where you like don't use effects and all these sorts of things, right? I think more and more so nowadays, I'm thinking about it. Okay, I mentioned I think about it as a technique for programming. Okay, but I think more and more I'm thinking about it as like it's a separation between how and what. It's like functional programming languages generally make it easy for you to give high level specifications for what you want to happen, right? Without caring too much about how it happens,
Right.
right? And okay, user schedulable languages are an example where this idea is taken like all the way out to the point where it's like very explicit. Okay, where in these languages you specify what the computation is that you're trying to do. Okay, and that could be, for example, some sort of like matrix multiplication or who knows what, right? Like some sort of like
Image
take these
processing
values and
kernel is
combine this.
classic. Yeah.
Yeah. So and then they separately say, okay, if you want to control the performance of this thing, you write a different, it's essentially like a DSL almost for talking about scheduling and performance optimization, right? Where in that DSL, you describe how to execute that computation. And crucially, in the DSL, the hope is that you're actually able to tune it for particular hardware, and it's easy to reconfigure it for different hardware, right?
Right.
So if I want to take this program, the what of the program is set in stone. Like, what does the program do? It multiplies two matrices, okay? But like, now the question is, how does it multiply two matrices? And that's going to be different on different hardware.
Right.
And you can write different configurations for different hardware that performs extremely well on different hardware, right? So I think this is a cool area in this space. But I think more generally, like I really like this idea of separating the how from the what. And I think about high level programming kind of in this model a lot these days, where it's like the details of how you specify like the how,
Yeah.
the mechanism by which you like
Express how.
execute it, yeah, the expression of it is
Yeah.
different in many cases, and sometimes it's like baked into the source code of the what.
Right.
But it doesn't have to be baked into the source code of the what. They can be just I don't know. So there's a lot of like there's opportunities to like play with this in the language design space. But I think at the very least, being able to say that I have a high level specification for some sort of computation, but I'm not going to dictate exactly how it gets computed is like really powerful.
I think
And
we're really getting into like almost user usability type things here because like at a really rough approximation, separating the what and the how is like some functional programmer hacker, they type up their functional program and then they fork the compiler that they're using and then they add some optimizations that are specific to their code and that for them is separating the what and the how. And like
I
what
was going to point out that compilers are a way to separate the what from the how.
exactly, like the compiler is the how part, and it's very complicated, so most people don't do it. But
yeah.
like you could have some language that lets you more easily hack on the compiler, and that's sort of what we're getting at here.
Yeah. I mean, the EXO compilation stuff actually maybe
Yeah.
is kind of in that direction,
Ah,
right?
I see.
It's the story, at least, of the EXO compilation space where they say, okay, there's all these compiler optimizations that you could do, like moving, this piece of code here and like retiling this loop in this way and these sorts of things.
Right.
Well, what if you just like handed those to the programmer and said like, all right, it's your job to optimize it now, right? But actually, I don't mean to bash that work. I actually think this is
Right.
a great idea. That's a fantastic idea. It's
Yeah,
like
yeah.
it works really well. And if I wish that I had like a way of safely composing optimizations, I could just say do this optimization and then do this optimization and blah 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 blah. And that's essentially what that work is trying to do, which is really cool. It's amazing.
Yeah, it's very cool.
Yeah, I was just writing a tutorial for EXO. That's what I work on these days. And so one of the challenges when you have this kind of low level way of specifying what you want to do to your program is you essentially end up writing a compiler or you write basically the compilation pipeline for each program, right? And so your users have a lot of control, but the control has a cost, which is that, of course, they need to do all of it, right? There's sort of a deeper problem here, which is we want our computational specifications separate from the physical realization of that. And we have a stack. We have the language, we have the compiler, and we have the hardware. And the responsibility of who manages sort of resource usage well needs to be somewhere in that stack. You cannot make it disappear, right? Like if you make your hardware simple, right? Like there was a lot of interest in building sort of much simpler hardware with the idea that functional programming languages have all of these nice properties and we're going to just sort of make them go fast automatically. That doesn't happen because that complexity now goes in the compiler somehow, right? Like VLIW scheduling was a big example of this. And VLIW scheduling is popular in particular domains, but in those domains, you end up writing very different kinds of programs that are intrinsic related, right? Or you build languages like user schedulable languages like Halide and Exo that can actually do this for you, but your compiler, and that simplifies your compiler, that simplifies your architecture, but now your language is very complicated. Or you could go all the way to what we had been doing for 60 years, which is your language is simple, right? Your compiler is simple, and then your hardware is a thing that discovers parallelism for you. Like there's no silver bullet. There's this like trifecta that like the control is going to be spread out somewhere, the realization of that control. And you have to like, I think the point you're hitting is like, there are many different options and for different users, there are different answers, right?
Yeah, and for different use cases as well, right?
Right.
But like I think usually the decision of like which technique you use in order to get what you're trying to accomplish is driven largely by like some sort of economic factor, right? You know, like one of the advantages of parallel functional programming that I've worked on is that you can write a like pretty efficient program really quickly. Like we can teach it to undergrads in like a few weeks, and they can write stuff that is within a factor 2 of like hand optimized C code, you know. Excellent, right? So now we have like, it takes you 1 hour to write something that's pretty fast, right? But maybe in a different economic world, you're like, okay, actually optimizing 1% is millions of dollars of value or something. And that's like a different, it's like a different space, right? And so there's like all these like decisions that I think pop up that are really important to keep in mind, you know, in terms of putting this in context, right? I think one of the big potential gains of like high level programming for performance sensitive tasks is the fact that you can write things that are fast quickly. And like usually developer time is the most expensive time. So that's like, you know, probably a useful context for like why this seems valuable, you know.
Yeah, and just to add some flavor to this, like optimizing one program is the most important thing. I mean, circuit design, which is the area I work in, is like this, right? Like before you ship out your final chip, you run your sort of compilation flow thousands of times so that you can sort of get the design that is randomly like 2% faster because the compilation problem for circuits is much harder. It requires like simulated annealing and all sorts of randomized algorithms. So like you have a lot of incentive of firing thousands of runs of your compiler so that you can get a design that's 2% faster or 2% smaller, so you can fit more things and you have a higher yield and blah, 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 right?
Right. Also because you're going to be printing the circuit board like how many times? And so might as well get the design good before you start printing it, right?
Exactly. And the other side of the economics of like compilers is, for example, the TPU team, the Google TPU team has decided that compiler compatibility is a primary concern in the architectural development of TPUs, for example, right?
Really?
It's like a real nod to the fact that like we have invested a lot, like building compilers is a really hard problem, and we should build architectures that can really co-evolve with the compiler. We can't just like, with architecture research, oftentimes there's a temptation to like look at workloads and be like, if I like add 2 latches here and 2 registers here and a FMA unit here, my workload is faster. And that's true, but no compiler can target that, right? There's this thesis from a long time ago on this VLIW machine compiler called the Eli 512 from Yale. And the compiler was called Bulldog. And there's a beautiful line in it about how they were trying to add a new architectural feature, but the compiler author told them that if you add this feature, my compiler needs to do backtracking search while compiling your program. And so that was enough to convince the architects that this was a bad idea, right? And so I think like when we think about designing compilers and languages in context of real problems, it needs to happen with real constraints like we have TPUs, we have invested a lot of money, we got to keep evolving them, but we can't just like dramatically change the architecture in a way the compiler has to change. And this is coming from Google, which has the resources to and the expertise to build compilers, right? So I think that's really interesting stuff.
Yeah.
Yeah.
Well, hey, I see in the chat somebody's asked if I've talked about entanglement yet, and I actually haven't. So do
Yeah.
you guys want to get into that a little bit?
Yeah, we better get. I mean, I
Yeah.
don't know if you have to leave anytime soon. It's been, an hour and a half. But if
I'm
you're
good.
excited to ready to talk about entanglement, I'm ready to hear about it.
That's right.
Yeah. Yeah. So yeah, we're kind of like coming back to some of what we've been talking about before in terms of garbage collection and parallel functional programming and all of that. But this was really my thesis topic was entanglement, or really the absence of it. So we call it disentanglement. Okay. So that's this was like the title of my PhD thesis. Okay. So uh, I think this fits into the story, by the way, though, because it's really about like co-design of language and high level programming and everything. And where the inspiration for this work came from was I went and looked at a bunch of parallel programs that were being written by researchers in like the parallel algorithm space. Okay, so these were people developing like high performance parallel algorithms for complex problems like graph processing and these sorts of things, where you have a lot of like interesting irregular parallelism. It's something where like the fork-join model that we talked about earlier is actually a really fantastic model for it, because you can have input dependent parallelism, you can have parallelism depends on randomness, you can have all sorts of like fun features, and then you have a scheduler that'll manage it for you efficiently. Okay, so looking at all of these programs, I think there was something interesting I noticed, which was that all of them had a certain discipline to them about how they used memory and how they used mutation. And disentanglement turned into this kind of like our attempt at characterizing what this discipline is. Or this was my attempt, at least, at like kind of characterizing what this discipline was. Now, I think the disentanglement idea really came originally from my advisor. Like, it was an idea that he had looking at functional programs and how functional programs interact with memory. Okay. And it was this observation that functional programs have very local management of memory. Like if you think about, and by local management, what I mean is like, if you think about what does a program do? It allocates memory, it initializes that memory, and then that memory gets used somewhere else by other aspects of the program. Okay. Functional programs have this tendency to kind of like locally use something and then get rid of it. It's like a very kind of like local property in the sense of like, maybe it's contained within a particular function call and these sorts of units of our programs, right? Like a function, right? But crucially, it's like attached to the computation somehow. Like if you start some sort of subroutine, then that subroutine has some sort of memory that it needs to access, and then it's done with that memory as soon as the subroutine is done, and you get rid of it, okay? So then let's extend this idea to parallel programs. And you can see that like these kind of like local compartments of memory use are independent of each other. They don't interact with each other. And the kind of interaction I'm talking about here is what we call a cross pointer, but it's where you have two separately allocated objects in memory that are allocated by parallel tasks. Okay, so two things running in parallel. I allocate something over here, and Rachit, you allocate something over there, right? At the same time. And now somehow we acquire pointers to each other's memory that we've allocated, right? This is what we call entanglement. Right. And the first cut was, if you look at pure functional programs, parallel functional programs that are pure, this never happens. And you can actually prove that it never happens, because it turns out that you need to mutate memory in a particular way in order to kind of like communicate that memory across the gap.
Yeah.
So my PhD thesis was taking this idea and extending it into the space of programs that also use mutation. And so going beyond pure functional programming and now saying, how can we characterize what this disentanglement property is, okay, at the level of memory mutation, or like just really kind of in general for like general programs, right? And what I found is that like this property disentanglement, where you don't have these cross pointers, I was finding it in programs that people were writing in C++ for parallel algorithms research.
Right.
You know, like it seemed like it was something that was there anyway. Like even if you're not in a functional language, it seems to be there. It seemed to be something that we could use. And so in some sense, I feel like the research that I was doing was not strictly purely about functional programming. It was like kind of going beyond functional programming. It was asking like, what is this property and like how can we use it, right? And it just turns out that like the application for it that we like really found to be compelling was for parallel functional programming.
Right.
But anyway, lost my train of thought. So I was talking about like disentanglement, like it was kind of already there and we were just trying to take advantage of it. We were able to take advantage of it for garbage collection, basically.
Right.
And we were able to figure out how to design a parallel garbage collector that relies on this property in order to get good performance. But then what we did more recently, this is just at PLDI 2023.
I was there.
Yeah.
It was right after me.
Yeah. So my friend Jatin gave a talk on our most recent version of this line of work, where we were able to take this property and extend it into the space of kind of arbitrary programs, even programs that have entanglement. So entanglement is when you cross the gap. It's when you have a pointer between parallel tasks. And we were able to figure out a way of automatically handling those cases with some overhead, okay? But still providing a cost model that lets you reason about like how, if I create these, how expensive is it? And then if you have stuff which is still disentangled, so if you have memory that is not reachable from some concurrent task, that memory is still handled efficiently.
Right. And so you actually sort of I think this is sort of a very clean idea and sort of, you know, when you describe it to someone, you're like, yeah, of course, this is a good idea, right? But I think it's important to point out this thing you mentioned, parallel garbage collection, right? Was not something we've really discussed up till this point, but it's part of the runtime. And of course, if you have a parallel runtime, you want your garbage collector to be parallel for reasons that you'll tell us. And it happens to be a really, really hard problem. Like parallel garbage collection is like one of those things when you start looking into it, you normally you think of it as like a solved problem somehow, but like you look at it in depth and you're like, it's not solved. Like we don't know the right way to do it. We don't know the right way to do it for a lot of different kinds of programming models. So I'm wondering if you can just give people context about like, why do we care about parallel garbage collection and why is it so hard? Like, why is it so freaking hard? To give some flavor on disentanglement. Yeah,
absolutely. So, I mean, the real challenge comes down to the fact that whether or not a piece of memory is garbage. So we say it's garbage as soon as we know for sure the program is not using it anymore. And that means it's not reachable by following the memory graph, following the pointers in the memory graph, okay? That's a global property. That's something which, if one thread is generating objects and another thread is pulling them out of a queue and manipulating them or whatever, you need to have global knowledge about the threads in your system or all the tasks in your system in order to be able to determine whether or not an object is garbage or not. And this is what makes parallel garbage collection so challenging. In order to figure out what's garbage, in some sense, it feels like you need all of your threads to communicate with each other, right? And some of the most successful techniques for parallel garbage collection are actually really dead simple. It's called stop the world, right? You literally pause everything in the program. You ask everybody, hey, what are you currently using right now? Like, tell me what you currently need access to. And then the garbage collector will go and trace the whole memory graph based on that knowledge. Right. And then you'll then restart your program. Not restart, but you'll resume the program by letting all your threads resume, whatever.
And to state the obvious, this is going back to our coordination problem. This is coordination. This is coordination of the entire parallel runtime that stops everything and adds a sequential dependency. And it's worse because it's an unexpected sequential dependency. You can't account for it. The garbage collector just decides, okay, the memory pressure is too high, I'm going to stop it. Or there's some like other set of abstract constraints that you as a programmer don't know about. So stop the world collection is really, even though it's a simple idea, it's sort of not necessarily the most pragmatic solution in this space, depending on what your workload requirements are.
And
Exactly.
it's going to be
And
especially expensive if you have lots of processors. Like, it has to stop all of them.
yeah. Like I think this is the biggest like point to make actually. If you only have 4 processors in your system, stop the world actually works really well, right? But it's fundamentally non-scalable. If you like imagine the future where everybody's laptop has 100 cores. I mean, we're actually already pretty close to this. So let's imagine even further into the future. Everybody's laptop has 10,000 cores, right?
Sure.
Okay, if we count GPUs, maybe we're already there. But anyway, my point is that like take this out into the future. Like this technique just doesn't work anymore. Eventually, it's just not applicable. It's gonna like completely ruin the performance of your program. Okay, so then people figured out, okay, you can do. There's a technique called concurrent garbage collection, and the idea with concurrent garbage collection is you try not to really stop anybody. So you have your threads running in your program. You try to not really like interrupt them. Okay, you periodically collect as little information from them as you possibly need. And then you just let the garbage collector run in the background where it's basically just walking through memory constantly. And it's figuring out on the fly which things become garbage and collecting them. The overhead of this is really high. The overhead of concurrent garbage collection in general is very high. The reason is that you need the garbage collector you need to like tell the garbage collector about every mutation that happens in your program. Like every time you change a point, you need to make sure the garbage collector knows about it. Because if the garbage collector doesn't know about it, it's not just a matter of like, oh, it might keep something alive that is actually garbage. It's actually that it might reclaim something that it shouldn't, right?
Right.
So there's this like fundamental problem where you like have to communicate with the garbage collector too much. And in our space for our work with this disentanglement property, what we were able to figure out how to do is local memory management. It's possible when so if you don't have these cross pointers between parallel tasks, then your tasks individually can do garbage collection only on their own memory without interfering with anybody else's memory. So this is a scalability property for garbage collection.
And the scalability comes from the fact that the garbage collector can mimic the fork-join structure of your computation in some ways.
Or it can like witness it. It can like
you could witness, yeah.
The thing that we'll tell the garbage collector about is the fork join structure, but that's pretty much all we have to tell it. Like, and the overhead of doing a fork, attach just a little bit more overhead on top of that, where you like tell the garbage collector about the fork, and that's pretty much it. And it turns out that the number of forks and joins in your program is like orders of magnitude smaller than the number of memory mutations you do, right? Yeah. So this works pretty well.
There's a relevant question in the chat about this, which is, so here's the question. With your disentanglement-aware GC, it sounds like you can dynamically determine when a state is disentangled, but is disentanglement statically analyzable or not?
Yeah. Okay, so there's a lot of cool stuff in this space. So first, let me say yes. Like our GC dynamically detects entanglement and handles it. And we actually have a paper at ICFP in 2022 where we show how to dynamically detect entanglement efficiently. So now let's talk about static guarantees. Okay, so here's the first, like, let's just make some observations, right? If we get rid of mutation entirely, then you get disentanglement for free. So this was like going all the way back to the origins of this work, where it was like, oh, if we look at pure parallel functional programming, it has this cool property. Like, okay, great. So like that's like a guarantee, a static guarantee that you can get by restricting mutation in the program. All right, let's loosen this a little bit. So if you have race freedom, but I'm going to clarify a very particular kind of race freedom, which we call determinacy race freedom. Basically, you have forks and joins, right? If you fork, that creates parallelism. All right. Now, just like keep track of what memory each task is reading and writing from. This determinacy race freedom property says that two things that are happening in parallel should never conflict on the same memory address. And conflict here means like one of them is modifying it while the other one is reading it, let's say. Okay, so this is like, that's what we call a determinacy race. By the way, the name determinacy race is suggestive because if you don't have these, then you can prove your program is deterministic. even with parallelism.
Right.
Assuming no other sources of non-determinism. So,
yeah.
But one consequence of this is that if you like have two threads that are competing to take a lock, that's a determinacy race.
Right.
Right. Okay, good. So we're clear on what the term means, at least. If you have determinacy race freedom, so you don't have any of these kinds of races, it turns out you have disentanglement. And this is the thing that we like. This is when I was really convinced that like this idea of disentanglement was like real, because you go and look at parallel programs that people are writing. Determinacy race freedom is a great property to have, and it's very common to find it like not just for performance reasons, but just to make it possible to like reason about your code.
Right.
This determinacy race freedom. So it like if you're in a context where you have mutation and you're modifying memory and everything, determinacy race freedom is a pretty good condition to try to guarantee. And like including avoiding contending on locks, although that's a whole separate topic that we could get into. But I mean, those are problematic for performance for a different reason. But so that's an opportunity for statically guaranteeing disentanglement. Like, and more concretely, like there are techniques for statically figuring out that a program is determinacy race free, like separation logic and these sorts of things, where you can like analyze programs and figure out like, okay, yeah, they actually have this race freedom property. Or there are type systems which can guarantee it statically, right? Yeah, I remember I was walking down the street. I was going to dinner. I remember who I was getting dinner with. And I was like halfway there. I was on Highland Avenue in Pittsburgh. And I had this light bulb moment of like, oh, like determinacy race freedom implies disentanglement. Like it was like this kind of like, like, and I remember like, I was like, shoot, I'm not gonna be able to pay attention at dinner now because this is all I'm gonna be thinking about when but I remember like as soon as I had that light bulb moment, that's when I was really convinced that this disentanglement idea was like really gonna work.
And this is in your most recent PLDI paper?
No, so that's from my 2020 Popple paper.
2020, okay.
Yeah, so that paper was like the paper where we really introduced this disentanglement property as like a formal, we gave a definition for it and we proved this determinacy race freedom connection and everything like that.
So you can still have mutation, but no determinacy races. So like no locks, no mutating someone else's memory where they could read it before or after, that sort of thing.
Yeah, that's kind of like the general mindset. So I should mention that like it's actually really quite easy to write parallel programs in this discipline. It might seem like it's hard, right? But I think it's hard if you're in the wrong programming model. And I think if you're in a programming model like, one of these like fork-join programming models, right? Where the scheduler just handles everything for you, right? All you have to think about is like just generating a bunch of tasks that do independent computation, right? And everything else is just handled for you. The scheduler schedules these things, synchronizes them for you automatically. Then writing determinacy race-free programs is actually not hard, like even if you're using mutation, because it's usually like really simple kind of reasoning like, oh, I'm doing a parallel for loop between 0 and n, and I give a unique index I to n different tasks, okay? And each one modifies the ith position of this array.
I see.
Yeah.
So you can mutate like the parent's memory as long as you sort of separated it already in your mind into disjoint pieces.
Yeah.
Okay.
And this really
That's very useful, right?
Hopefully, I mean, this should make it clear the connection with separation logic for anybody who's familiar. I mean, like, use separation logic to prove that your program is race free. Well, maybe then you get disentanglement for free out of that too.
Yeah,
right? You prove that it's race free, and now you know that it's also disentangled, so you can take advantage of all these memory management techniques that we figured out. Yeah,
that's a neat connection. Yeah. Did you have to go, Ratchet?
Yeah, I do have to head out soon, but I guess I had one wrap-up thought about sort of the effective, like things that end up being effective reasoning tools or principles in PL are often things that people are already doing in the wild, right? Like the ownership model in Rust is something that I often think about as a good example of this, which is it's an enforcement mechanism of a programming paradigm that people already try to use because it's easier for reasoning and building scalable systems and doing all of these all of these things, right? And so I think like this concept of disentanglement really also follows the same path, where it's like people already want to do this because it's easier to maintain programs like this, right? Like when you can use ForkJoin, you should use ForkJoin because it's a good programming model, right? Because it's much nicer than some of these other parallel programming models that really have to contend with things like lock, contend with locks. And so like the cool thing about this work has always been that like you found this in the wild and you could sort of formalize it, and now you can go back and build tools that enforce it as a mechanism in the language. So like one thought I've always had is like this is something that Rust could possibly do, or like an extension of Rust with sort of a stronger reasoning capabilities, where you can enforce the fork-join structure. And then when you run it with a particular runtime that requires your program to implement some trait that says, I'm a fork-join program, that runtime can sort of enforce disentanglement and sort of use that to do more efficient scheduling and reclamation, stuff like that.
Absolutely. Yeah.
So it's been really cool. But yeah, this was an absolute blast. I feel like I could just keep talking about this for hours on end. Thank you so much.
Sure.
Yeah, I could too.
For starting this off. We'll try to have you again, I guess. But I think at peak we had something like 20 people, which I think for the first show is like
wow, that's
really, really good. And I think I really enjoyed the questions from the chat. We'll try to do a better job of like pinning some topics where I'm still getting used to Twitch. So next time we'll try to do a better job about like pinning the topics we're talking about and having people ask more questions. But the interactions we had was already super great. So yeah, thanks for coming, Sam. You mentioned you're going to go on the academic job market. If there's someone in the chat who this is relevant for, please keep this in mind, and Sam will obviously, after this show, you should be convinced we'll make a great addition to your team or faculty or whatever.
Thanks, Richard.
Yeah,
thanks so much, Sam. Great to have you.
Yeah, thank you both for inviting me.
Oh, and next week we have our next episode of the TheForkJoin. Usually it'll be every 2 weeks. Because of scheduling, we have Harry Goldstein coming on in 1 week. So look out for that, everybody.
He will tell us about property-based testing and all the cool things people have been doing with it. So please do stop by. Yeah, thanks for coming, Sam. We'll see you. Have a good day. Hope you enjoy the sunny Pittsburgh weather. Hopefully it's sunny. Yeah. All right.
Absolutely. Thank you, guys.
Bye-bye.
Bye-bye.